So you can write down this definition of sample space. That's the formal definition. I would say maybe something like this would be really helpful. I always think of it as success. Probability is success on top, and the total possible options on the bottom. Now formally we call this S as the sample space, and you count the number of all the elements in S in the denominator there. So let's read this question. What is the probability of having at least 2 heads when you flip 3 coins? So let's think about the sample space of flipping 3 coins. So list out all the possible cases here. So heads, heads, heads is one possibility if I flip 3 coins. Heads, heads, tails. Heads, tails, heads. And heads, let's see, tails, tails. There are 4 possibilities to start with H. Let's do the T's here. So T, 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 H. Tails, heads, tails, and finally tails, heads, heads. So we have 8 different possibilities. Those are all the elements in the sample space. So in the denominator of our answer is going to be the number 8, right? Because there are 8 items down there. There's another way to get that if you wanted to. There's really, you're flipping 2 coins or 3 coins, so there's 3 events here. So if you did kind of a, if you think about the slot method here, you've got 2 outcomes for the first coin when you flip it. You get 2 outcomes, heads or tails for the second, and same thing for the third. 2 times 2 times 2 is 8. That's why there's 8 items in the sample space here. So that's where our 8 elements of the sample space go in the denominator. Now what are we looking for? At least 2 heads. So how many of these have at least 2? This one has exactly 2 heads. This one has 2 heads. This one has 2 heads. And this one has at least 2. It actually has 3 heads, but that would count. So there are 1, 2, 3, 4 out of the 8 cases. So that would be 4 out of 8, which is 1/2, which is 0.5. Either answer is acceptable. Some students like to write decimals, some fraction, simplified form. Either one is okay. There's another question here, very similar. This should be easy if we, since we have the sample space written out. Really helpful to write out the sample space. What's the probability of having no heads when you flip 3 coins? So there's only one case that has no heads, and so that would be 1 out of a total of 8 different cases. So then you type that in your calculator to get the decimal, and you write the decimal there. Again, simplified fraction or decimal is acceptable in this section. So 5-card poker. So before we start, I just want to mention a couple things about cards. 52 cards in the deck. There are, let's see, 13 spades. That's one of the suits. There are 13 clubs. There are 13 hearts. And there are 13 diamonds. And so you can probably tell that I did these on purpose. Half the cards, or 26 of the 52, are red. 26 of the 52 are black cards. So there are 4 suits, 13 in each suit. In each suit, like, there would be some face cards. So Jack, Queen, and King are all face cards. Ace is not a face card. Those are the face cards. So each of these 4 suits would have a Jack, Queen, King, Jack, Queen, King, etc. There'd be 12 total face cards. The numbers start at 2, 3, all the way up to 10, then Jack, Queen, King, and then Ace being usually the highest card. And so all suits would have those same 13 cards. Poker, you need to know a little bit about poker to answer these probability questions. Poker is a game where the order you get the cards in doesn't matter for regular 5-card poker. So what I mean by that is if you get an ace card first or ace last, it doesn't matter when you order it. Usually you reorder your hand anyway. You organize it however you want. So order you get the cards in doesn't matter. So we're going to use NCR. It's going to be a combination here. So we're going to use combinations because order does not matter with poker. We're also combining the idea of probability. So success divided by total here. So let's think about the successful. Well, I think about the total first. So we're going to use NCR. So what's my N and what's my R here? So N is the total possible things here. So we're choosing from 52. And we don't just want one card. For poker, it's a 5-card hand. So 52, choose 5. So then to figure out that number, you can bring out your calculator. And sorry about that. And you can type in, say, a scratch pad here. So we're going to say, hit the menu key on TI Inspire, probability. And then it's a combination. NCR is a combination, so NCR. And you're going to say 52, commas in the bottom left-hand corner of the screen, comma 5. It should be like over 2.5 million, I think. Yeah, 2,598,960. So 2,598,960 or something like that. So that's the number. You have over 2.5 million hands that you get in poker. But success, we want to get all spades. Well, look back to spades. There are 13 spade cards. So we need to get all spades. So with my NCR, it's going to be 13 winning cards. I don't want just one of those. I want 5 winning cards. I want 5 spades. So then you get your calculator back out and type in, menu, probability, combinations, 13, comma, 5. And you get 1287 here. So 1287 is the number. That's the successful outcomes. There's 1287 of them. Use your, I would probably prefer, a decimal makes more sense here. I think when you do that in your calculator, it ends up being somewhere around 0.0003, 12 or something like that, that maybe 4 digits. But a 0.03% chance, basically, or 0.04, I forget exactly what it was. Let me do it. So it would be this number divided by this number. And let's get the decimal there. Whoops. So Control Enter, so we get 0.00495. That's what it was. 0.00495. So here we go. So 0.00495. So just over a 0.04% chance of that happening. It's not very likely for that to happen. Let's do this one real quickly. You're trying to get some defective tennis balls, so let's do NCR. We don't care the order the balls are picked. So in this one, it would be NCR 20, and you're choosing, it looks like we're choosing, if 2 balls are selected, so 20 choose 2 tennis balls in the denominator. In the numerator, we want to choose defective balls. We want both balls to be defective, both tennis balls defective. There are 4 defective ones, so of the 4 defective ones, I want to choose 2 of those. Type that in your calculator. You can type it in as a fraction, and you'll get your decimal answer. I think it ends up being 0.03 something, and then you'll go on from there. So now we're going to talk about independent events here. So independent events are 2 events that have no effect on each other, like rolling a die and flipping a coin. If I roll a 5, I still have a 50% chance of flipping a heads or tails there. It has no effect on each other. So all you do for independent events is multiply the 2 events. And this is for an OR type statement, or sorry, an AND type statement. So this is intersection, is what that symbol means. So we're saying AND here. So a jar contains 5 red balls and 4 black balls. A ball is drawn at random from the jar and then replaced, and another ball is picked. So because the ball is replaced, these 2 events are independent. In other words, you reach into a bag, you shake it up, reach into it, pick one of the 9 balls in there. 5 are red, 4 are black. You put the ball you just picked back in the bag, shake it up, and pick again. You have the same 9 balls. It's the same chance. Nothing changed. One pick has no effect on the other. Because you replace the balls, these are purely independent events. So we're just going to multiply, because we want 2 reds. We want a red and a red, so it fits the form here. So we're going to multiply the probability of red times probability of red. So let's do that. So probability of red times probability of red. Well, 5 of the 9 balls are red. So 5 over 9 times, if I replace the ball, it's the same probability again, 5 over 9, which ends up being somewhere around 25 over 81. Now if I change this problem slightly and I said, okay, we're not replacing the balls. So once you choose a red ball, it's out of the mix. no longer is this an independent event because your first pick had an effect on the second pick. So if you don't replace, it absolutely is not independent. It is a dependent event. So let's figure out that. It's going to be a slightly different calculation. You still multiply. So the first probability is 5 out of 9. That doesn't change. But if the first ball you picked is red, now there's only 4 red balls left. 4 out of, and don't say 9, you picked a ball and you didn't replace it. So there are only 8 choices. So the answer here would be 20 over 72. And again, you want to keep simplifying. 10 over 36, or 5 over 18. Keep simplifying until you get a simplified fraction, or you can type in a calculator and get a decimal would be fine. Union of 2 events. So this means an OR statement here. So this is an OR statement. What's probably the card drawn at random from a deck is either a face card or a spade. Because this is just one card. We don't talk about it. This is a permutation or a combination. It's just one card. Right, so I'm going to draw this. I think it'll make a lot more sense if I draw it as a Venn diagram. So in this case, we're going to say these cards are face cards, and these cards are spades. So to picture this really helps us understand. This is the weird part of the formula. This is kind of like the, that's an AND statement there, by the way. This is like the overlap of the graph. And we have to subtract it out. I want you to understand why we do this formula. Okay, so for this one, let's see. The way a Venn diagram works, this is the overlap. Are there any cards that are face cards and spades? If you think back to this, right? Spades, there's 13 spades. 3 of those cards are face cards and spades. The Jack, Queen, King of spades. So we have 3 cards that are both face cards, Jack, Queen, and King of spades, and spades. We know there's a total of 12 face cards. So 3 of them are spades. 9 of those are not spades. So you have 3 diamonds, 3 hearts, 3 clubs here. There's a total of 13 spades, but 3 of them are face cards. So 10 of them are not face cards. So I have 13 spades. I have 12 face cards. That's a beautiful picture of this. So what we're doing with this is we're saying probability of the first event, face cards, plus the probability of the second event, spades, minus the probability of the overlap. So the reason we have to do that overlap is this. When you figure out that first probability, what's the probability of 10 face cards? So that would be 12 out of 52. Plus, what's the probability of getting spades? So how many spades do we have? We have 10 and 3 here. So we have 13 out of 52. Minus, according to the formula, I have to subtract the overlap of this. So the overlap is the AND. That's that little part in the middle. The reason we have to subtract it, to get that 12, I did 9 plus 3. I counted those Jack, Queen, and King of spades. To get this 13, I did 10 plus 3. I counted those Jack, Queen, and King of spades. Again, I counted those 3 numbers twice. I have to subtract the overlap because I counted those things twice. This would be 25 over 52 minus 3 is 22 over 52, which is 11 over 26. Type in your calculator if you want the decimal, and you've got it. So I think the Venn diagram is almost easier. In fact, if I were doing this problem, I might just draw a picture of it and not use the formula so much as just say, well, how many cards are in here? 9 plus 3 plus 10. I didn't double count the 3, I just counted it once. 9 plus 3 is 12. 12 plus 10 is 22. 22 out of 52 cards is the same answer I get over here. Last idea is this idea of a complement. 2 things are a complement if they're the exact opposite. So look at this example here. What's probably picking blue is a very easy question. It would be 1 out of a total of 3 marbles is blue. But that's the complement of that. The complement of picking blue is not picking blue or not blue. So what's the probability of not picking blue? There's 1/3 chance of picking blue. If there's 2 red and 1 blue, there's a 2/3 chance of not picking blue. So the probability, these 2 things add up to 1 or 100%. Picking blue, not picking blue, they'll add up to 100% every time. That's why if you think about this, the probability of event plus the probability of its complement always add up to 1, or they always add up to 100%. And that's what this is saying. And sometimes on a very difficult problem, we'll actually use this theorem to help us out. That's the end of the lesson today.